getting it wrong?
Whatever works, but yeah, as long as the microphone's near your mouth. Yeah, you can. So you can do it this way, kind of over your ears.
Oh, okay. Yep. Thank you. To change, I just push.
No, that I'll turn it off. So that just goes in your pocket, and then you can use the arrow keys.
Oh, arrow keys. Should I turn it on?
Thank you.
Okay.
First talk is given by Jerry. The validation of the wall-bounded high-random number flows using manifolds and vectors.
Thank you very much for the introduction. So I will start with my agenda for this talk. So here I am trying to validate the turbulent channel case for the high Reynolds numbers. And I'm using the wall laws. and how we realized this wall law in lattice-Boltzmann context. And I have also chosen 4 different kinds of collision operators in this study. So I will give brief introduction about them, and then description about the periodic channel, and then validation with respect to direct numerical simulation data and challenges. So the motivation for my this study is that previously there was a study conducted by Karazis and others with the industrial partners to understand the fluid flows in the nuclear reactor core. Those are the fuel rods, and they are source of heat. When the water is flowing, it has to take the heat and give it to the secondary circuit. In these cases, the Reynolds number is very high. So for those applications, we wanted to simulate that. Previously, there was some study done by the few of the colleagues, and we wanted to explore it more and also make it run on the GPUs. For that applications, I'm trying to do the turbulent channel case validation as the initial step. And yeah, here in this one, Reynolds number is varying from 80,000 to 150,000. In those test cases, the Reynolds number that we are interested vary even more than 350,000. So to give the brief description about the wall law, the x-axis represents the distance from the wall. Distance from the wall in the sense from the y equals to 0 to y equals to 2n. So if from the middle up to the middle point, the distance along the y-axis, that is represented in this plot along the x-axis, and y-axis represent the velocity. And they are non-dimensionalized in the wall units. So the reference velocity in these cases is the friction velocity u tau. And for the distance y plus, it is scaled by u tau and kinematic viscosity. And wall is located at y equals to 0. And this is the blue line that represents the viscous sublayer, and the green line represents the log law. And in between, the transition has to be smooth from viscous layer to the log law. And viscous sublayer varies from 0 to 5. There, the flow is laminar. And in the log law, the velocity varies logarithmically with the distance. That is from y plus 30 to 300. And in the buffer layer, there is it has to be to smooth transition. So from DNS data, this profile can be seen. But if we try to make an analytical expression for the relation between u plus and y plus to derive boundary conditions, there are many in the classical finite volume solvers. There are multiple wall law profiles like Musker law or a Spalding law or a Reichardt profile. Here, but those are implicit expressions. So u plus is a function of y plus. If we see from here, u plus is also dependent on u tau, y plus is also dependent on u tau. So when both left-hand side and right-hand side are functions of the variable that we're interested in to solve, the equation becomes implicit. To solve that, we have to go for the Newtonian iterations in the numerical sense. For that, when I was trying to validate that, I was running into some problems. So I was exploring, is there a way to construct it explicitly? So I saw this paper from 2022 that was done by ANSYS and the collaboration with the university. They had derived this explicit Musker profile. Here they introduced a new variable that is R plus. One R plus, it's a multiplication of U plus and Y plus. So the U tau get cancelled. The entire right-hand side is completely known in terms of a known variables. The alpha, beta, they are just constants. So we can evaluate it directly. So I'm using this wall law for my wall boundary condition. So that was the expression, analytical expression for this curvature. And how do we realize this wall law in lattice-Boltzmann method context? So this boundary handling was proposed by Mangtao Han and others in 21. So how is this wall law realized in LBM? So no slip boundary condition, we do bounce back, as we all know. And for the free slip along the normal direction, we do the mirror kind of a reflection. So no slip specifies zero velocity, free slip del u by del y becomes 0. And in the wall function bounce boundary condition, what we do is we first apply free slip boundary condition. So there is no velocity, del u by del y is 0. After that, we compute the u tau and apply that much amount of drag force. How these authors has done is that they had used D3Q19 stencil and multiple relaxation time collision model. So they directly vary the PDFs near the boundaries for the D3Q19 stencil. So when I read that literature, it seemed it's very much hard coded into the given stencil. If I want to do for the D3Q27 stencil, it was not straightforward to extend it. So for that, I thought to just generalize this approach. And instead of modifying the PDF values, I will apply that much, because this is the force-driven channel. Near the boundary, I will apply that much amount of a drag force directly itself, so that this boundary condition satisfies. So I have implemented in that way. So, and also in this study, I have chosen multiple collision operators for the comparison purpose. First one is the single relaxation time with the Smagorinsky subgrid scale model. And second one is the two relaxation time with the entropic stabilization. Third one is the cumulant collision operator. For this, the 3, 4, and 5, those relaxation rates are 1. And for the fourth one, cumulant collision operator with the fourth order correction, for the fourth order correction, third, fourth, and fifth relaxation rates of a function of a kinematic viscosity. And I have used Smagorinsky subgrid scale model on top of that. So to give the introduction, brief description about the setup, the flow is going from x equals to 0 to the L, and domain size is specified in terms of 6 pi, 2 times, and 2 pi in terms of a channel reference length n. And it is the channel is driven by force, and pressure drop is given by u tau square by the half width, and that is converted in terms of a friction Reynolds number. So I'm using this forcing scheme. And I have tested this for the 4 sets of friction Reynolds number varying from 550 to 5,200, and corresponding bulk Reynolds number vary from 20,000 to 250,000. And I have kept the Mach number constant 0.125 so that we are in an incompressible regime. And depending on the reference time, I made a decision about how many time steps I run for initial time steps, then velocity averaging, and then Reynolds stress averaging. And in the LBM setup, I have already gave introduction about the collision operators. Stencil, I'm using D3Q27. And for the inlet and outlet, it is a periodic boundary condition. And at y equals to 0 and y equals to 2n, I'm applying the wall function bounce boundary that I explained before. And in z direction also, it's a periodic. And I'm initializing the flow field with 1/7 power law, but it's a laminar initialization. There is no initial turbulence. And now to see the validation results with respect to DNS data. For the DNS, I'm taking from Lee and Moser paper. And first, I'm comparing the collision operators for the largest resolution that I have chosen. And then I'm doing the grid independent study for 3 different resolutions. And then I'm comparing the relative mean squared error. In the relative mean squared error, I'm comparing all the collision operators for all the grid resolutions. And I'm comparing 3 fields here. For the presentation purpose, I'm comparing 3 fields: average velocity, shear stress, and turbulent kinetic energy. Although I had done study for the 1,000, 2,000, and 5,000 friction Reynolds number, they have a similar be comparing results. So I'm showing 2,000 friction Reynolds number as a representative of these 3 higher friction Reynolds numbers. So when I'm comparing the average velocity to the DNS data, when y plus the first grid point is around 20, all the collision operators show relatively good agreement with the DNS data. the cumulant collision operator with all the higher order cumulants relaxed with the relaxation rate of 1, that always show first point deviation from the DNS data in many different setups for y plus greater than 20. And if I compare the turbulent kinetic energy with 4 different kinds of collision operators, so they are also in a good agreement. Cumulant collision operator with all higher moments with the relaxation rate of 1, it is able to capture the maximum, because that point is little bit trickier, because that's the peak. It's able to capture that point. And when I use the Smagorinsky, it goes down. So Smagorinsky dissipates turbulent kinetic energy more rapidly. And yeah, and in the if I'm doing single relaxation times Smagorinsky, that one has a little bit over prediction compared to the DNS data, because even after those many time steps of averaging also, it wasn't a smooth profile. It has a zigzag pattern that we can see in the shear stress also. For the single relaxation time Smagorinsky, we can see that with zigzag, a little bit of a zigzag pattern, but other collision operators are in a really good agreement with the DNS data. And for the now for the one collision operator, I want to do grid independence. So here I have chosen 3 resolutions, reference length into 24 grid points, 36 and 48. And I'm comparing those results with the DNS data. From these slides, we can see that as I'm increasing the grid size, the solution is converging. It is becoming in a good, better and better agreement with the DNS data. And if I compare the turbulent kinetic energy with the different resolutions also, we can see that the converging behavior is getting better towards the DNS. And for the shear stress also, in the bulk, the agreement is good for all the resolutions. So as it gets grid size increase, we can see that it's able to trying to capture the sharp variation. And now let us see the relative mean squared error analysis. Here on the y-axis, it's L2 error, and here on the x-axis, it's resolution. So as I'm increasing the resolution, the L2 error is becoming better and better. The lowest error is for the cumulant collision operator with Smagorinsky. And as the error is in the, once it's in the 4% or 2%, for the highest resolution, it's getting closer in between 1 and 2%. So if it's 1%, 2%, then later it's harder to have to become better and better. It seems it needs even huge resolution. And for the Reynolds normal stresses and shear stresses also, I had made similar kind of plots. They also had shown with respect to increased resolution, L2 error decreasing. But from this, I cannot make a comment on the order of convergence, but we can see that at least it's getting better. And to mention the challenges observed, if I go for the friction Reynolds number of 550, the y plus value become less than 20. In those cases, the first grid point is in between the viscous sublayer and log law. In the transition zone, even from the literature review that I did, they mentioned that here it is harder to capture the profiles accurately. There will be more errors. So there will be more errors. That was the impression I got from the literatures. So how much error do I get? So I wanted to see that as well. So if I compare for the 550 friction Reynolds numbers, if I compare 4 collision operators, when y plus is around 6, first grid point is at y plus equals to 6, And the second grid point is y plus equals to 18, because first point is at 0.5 distance from the wall. So here we can see that I was trying to capture accurately at the first point, but it's getting over predicted. And in the bulk, it's getting under predicted. So if we see this without the log, the velocity gradient in this resolution, it's become very straight line. That's a very strong gradient. So that is harder for to capture for this numerical scheme at a given resolution. And for this one, all three resolution points lying in the transition layer between viscous and log law. So here it is harder to observe the convergence, but the error varies between 4% to the 5.2 overall together with all the collision operators. If from this plot, if we want to see the minimum error variation, the cumulant with Smagorinsky varying from 4 to 5%. It is 1% variation. And the TRT with the KBC models, it's from 4.5 to 5%. So it's 0.5% variation. In the transition layer, I can say it isn't bad, but if you have any comments on that one, please let me know. And to conclude my talk, we can say from these results that all the collision models have a good stability, because I was running into problem of stability as well many times. So they have a good stability for all the tested large Reynolds number, because the Reynolds number varies in this test from 20,000 to 250,000. And the idea of using the explicit wall law that is compatible with all the evaluated collision operators. And also we can say it is a successful generalization of wall function bounce boundary condition that was proposed for one stencil and one collision operator. And from the velocity profile results, I can say that accuracy is better when y plus is more than 20. Accuracy is very good at y plus greater than 20. In the transition zone, accuracy is not bad. And the next step is because here in this study, the grid points were axis aligned. When the grid points are non-axis aligned in the complex geometric cases, so I wanted to consider the periodic hill geometry or a wavy channel as a benchmark case and test these boundary conditions for this. And they also have a good DNS database, so I wanted to compare that. Yeah, thank you very much for your time.
Did you decrease the lot number with the resolution increase?
No, I kept it constant. You can ask why? Okay.
I was asking why something else. Why?
Okay.
Why is Smagorinsky in the boundary flow? You know that Smagorinsky overpredicts the equivalent kinetic energy right on the boundary. So if you want to study this, then and you put some Smagorinsky, some non-Smagorinsky in it, then you know the comparison is not so clear. Why did you use Smagorinsky for some of them, and why actually Smagorinsky?
Single relaxation time I have to use. Otherwise, I don't get stability. For the cumulant collision operator with omega 3, 4, and 5, if they are functions of omega 1, in those cases, from the first literature, there was a limiter coming into the picture. For it was dependent on the different resolutions and different friction Reynolds numbers. When I was testing for the 950, I was running into the stability problems. So I thought to include the Smagorinsky. Yeah.
Probably try to use something that is not another equivalence model that doesn't.
Probably AMD anisotropic minimum dissipation or a yeah. Yeah, I tried to see that, but compared to Smogorinsky, I couldn't observe much difference. I was like, I should observe. I was expecting that. But when I tried QR subgrid scale model, I couldn't make much decision about it's better. Ah, yeah. Thank you.
Actually, it's very clear, the hydrodynamic limit of the filtered Boltzmann equation. I just go.
Marson, yes,
And, you know,
and Malaspinas. I don't remember if there is a way to put it full screen. F11. Let's try. Yes. Okay. Hello. Thank you for the presentation. Indeed, this is a pretty explicit title. Before starting, I just want to show my very small group at the School of Engineering of Geneva. So my boss is Orestes Malaspinas, who is mostly known for the recursive regularized collision model, and also the one of the main developer of Palabos. And we are also in strict collaboration with the University of Geneva, the group of Professor Jonas Latt. So I want to start my presentation with this nice image from Philip Spallard at the Boeing Corporation. It is just the touch EDDY simulation. And why it's interesting for me is because it uses most all the ingredients we can use in turbulence modeling. So basically, we have our filter Navier-Stokes equation, and then we use either LES or RANS on the bulk or close to the boundary. So in the bulk of the simulation, we can resolve more turbulence case. So we can use like an algebraic turbulence model with LES. But when we get closer to the wall, we increase our turbulence modeling effort. And so we use a turbulence model with 2 or more equations that are based on Reynolds average Navier-Stokes equation. In this case, we also model the Navier-Stokes equation, a filter Navier-Stokes equation, filter on time, not in space, but still filter. So that's just a recap of the possible approaches to do a simulation of a turbulence flow. So we have our LES and RANS models. So that's why what we are using in the picture we have seen before. And of course, we can use DNS and solve everything, or we can use, as in the previous presentation, a world model. But yeah, both LES and RANS are based on the filtering operation of the Navier-Stokes equation. Here I have like a filter Boltzmann Navier-Stokes equation in the sense of LES. So basically, it's the Navier-Stokes equation that is applied to filter variables instead of being applied to our velocity, density, and pressure. So the effect of this is that we have some commutation errors that here is called as capital M alpha 1 alpha 2, which is the subgrid scale tensor. And here in black also we see the filter operation defined as an operator. So it's a convolutional filter. In the easiest case, it's just an average of each variable with the neighboring values of the variable itself. So how do we derive actually this filter Navier-Stokes equation? So given that I'm a very fastidious person, I will start from an axiomatic approach for our axioms of classical physics, so Newton's law, basically, plus assumption, of course, of interaction potential, so how the particles making up the fluid interacts between them. Then we apply some assumption and we get Navier-Stokes equation. Then we apply our filter to Navier-Stokes equations and we get our filter Navier-Stokes equation with these commutation errors. So now, what are these Navier-Stokes assumptions out there? So there are many. There are mainly because we do like a statistical interpretation of Newton's law somehow. So we have ergodicity, Boltzmann counting, for instance. But most importantly is this Newton's constitutive law assumption, where somehow we define the effect of the collision of the particles in the flow. So we define which is the shape of our stress tensor of the fluid based on some assumption. So these are some of the assumptions. So we assume that we can represent the stress tensor as a linear combination of the velocity derivatives, that there are no time or derivatives or integrals, there are no viscous forces, and the tensor is symmetric. So of course, this introduces very small errors that are negligible in our Navier-Stokes representation for Newtonian fluid, of course. But the question is that we can ask ourselves is, okay, are these errors still negligible always in all cases at the filter Navier-Stokes level? And or another question is it correct to do the filter, apply the filter at this level of our development of the equation, or should we apply it before when we are closer to our axiomatic way of representing the physical world and then apply the filter? And but in this case, can we still apply the Newton's constitutive law after the filter, for instance? So this is also a question, and this is a little bit less easy to justify, that we can simply apply this Newton's constitutive law to the filtered equation afterwards, so after the filter. So to answer a little bit to all these questions, what we can do is, okay, we can take another path to the Navier-Stokes equation, which is before we develop the Boltzmann equation, and only then we get to the Navier-Stokes equation solution. So in this case, we get exactly the same solutions. And what is interesting is also that like the Newtonian fluid model emerges naturally from the collision model that we defined for the Boltzmann equation. So here I mean a Boltzmann equation modeled with a relaxation toward the equilibrium model, like the BGK in the simplest case. So we can do also now an experiment and apply the filter before directly to the Boltzmann equation, and only afterwards taking this operation of taking the moments of our distribution function and the Chapman-Escog expansion and see what happens. And what happens, this is a spoiler, is that a Newtonian fluid model does not emerge just as before, but we have also some extra commutation errors. So the question is, do these extra commutation errors have any meaning, are relevant or are not? So that's a little bit my investigation. That's somehow just started. So this is a little bit the vision more in detail with our Newton's law and finally the Navier-Stokes equation here. So I represent some operation. We do manipulation of this equation with like this M. The M represent the operation of taking the moment of the Boltzmann the distribution function, and N is the assumption of a Newtonian fluid model. Then the second route, we go through the Boltzmann equation. In this case, we define a collision model. So a relaxation toward equilibrium collision model. Then we have the Chapman-Escog expansion, and again, the operation of taking the moments. Okay, here, so I represented all these operations like operators. And why to do so? Because I want to see if they commute. So what does it mean, they commute? So just refresh what it is, a commutator. So the commutator is an operator that tells us if the order of application of two operators is important or not. So if the commutator gives us 0, it means that we can switch the order of these two operations. So let's see a little bit what happens for the operations, the operators we have here in our derivations. So well, it's well known that taking the moments operation does not commute with the filtering operation, and that's why we have this subgrid scale tensor in the filter Navier-Stokes equation. But what about the other operators we apply? Well, actually, a priori, we cannot say they commute with the filter. So let's try to do, I want to show a little bit what I did on the work on the filter Boltzmann equation. So I really took the Boltzmann equation and took the filter and did the Chapman-Enskog expansion. So I did it also, this is a little bit uncommon, directly in the non-dimensional manner. So I non-dimensionalized the Boltzmann equation with two scales, macroscopic and microscopic scales. Then I applied the filter and did the Chapman-Enskog expansion of that. And the result is the following. So as you can see, is not as the standard filter, the Navier-Stokes equation, because that is the red part, but we also have some extra kinetic commutation errors, I call them here, that they seem scaled here from a max square over Reynolds term, but this is just a small parameter I'm using doing the Chapman-Enskog expansion. And they are not actually the scale of these terms. So we cannot say the real magnitude of these terms. These max square Reynolds just tell us that they come from the second order in Chapman-Enskog equation. So they are viscous somehow. So they come from the non-commutation somehow of the viscous part of the equation. So what to do to try to investigate these terms, if they are meaningful or if they are not meaningful. So I just did again the expansion, but in the dimensional manner, such as I can then try to get real dimensions for the terms. And the answer from now is no answer, because of course, I just did like a simple test case on a TGV, Taylor-Green vortex. And as expected, as I was expecting, the magnitude of these terms are very small. Otherwise, it could be we would have problems on standard Navier-Stokes equation modeling. So if we take on the left-hand side, you have the magnitude of the gradient of the subgrid scale tensor. And on the right-hand side, the magnitude of all the sum of all these terms. And we are at least 3 order of magnitude smaller, which is encouraging in the sense, okay, that's exactly what we were expecting. Still, I'm computing these terms as post-processing, and I'm still far from DNS. So these are really preliminary results. But what I want to say is that in any case, even going to a more serious simulation at the DNS scale, I don't expect to see these terms to become much bigger. Where I could see or expect or have the hope that this extra term perhaps can help us on turbulence modeling is close to the boundary, where the assumption of a Newtonian fluid model at coarser scale might not be so trivial. So a little bit the plan is to try to investigate the values or the magnitude of this extra kinetic term close to the boundary, and to see if we can use them somehow to improve the turbulence modeling in general. So this is the end, and I wait for your questions. Thank you. Yeah.
As I presented it in my talk, we attempted it on this class before.
Mhm.
And we run into issues. Then, I have a thought that, when you filter the molecular Boltzmann distribution function, it's not the appropriate distribution function to be filtered for, because that distribution function is not what we are looking for turbulence. Turbulence fluctuation is a different type of distribution. So you're starting from there. There's lots of analytical challenges, theoretical challenges. You end up with many extra terms. You can say all these terms are important or not important. But the fundamental question is, these extra terms maybe is just a manifestation of a wrong distribution function to be filtered. All right, that's the first comment. The second comment is, in turbulence, we, at least in the regime of our probability, we do not question the validity of the Navier-Stokes. All right. But when you filter the Navier-Stokes, we're running into trouble. All right. That's what the core of the turbulence model is about. So we should. That's my claim. I mean, you obviously did a great job on this. That we should start with a equivalent representation, which exactly reproduce Navier-Stokes. We don't question the validity of Navier-Stokes, so we don't do a Boltzmann, which is a one lower level filtering, but we filter the Navier-Stokes, but we don't. We try to construct a kinetic representation that it recovers Navier-Stokes exactly, and then we filter from there. I think that gives a more clear picture of it.
Yeah.
So that, we have a. I mean, I hope you understand what I'm trying to say.
Yeah. So just to clarify here, I'm not questioning Navier-Stokes. I'm questioning the operation of filtering on the part of the viscous part of Navier-Stokes. So I'm not saying that Navier-Stokes is wrong. DNS is perfect Navier-Stokes. So actually, we could try to compute. This is what I want to do. These commutation errors from also Navier-Stokes solvers. So yes, then the first question. I don't know if I did answer in case you tell me. The first question is if we have to take another distribution function in the case of turbulence, because perhaps it's better to do the modeling. Perhaps yes, but this is just the original distribution function. So I'm not introducing anything at all. We have some assumptions we made also, of course, in the collision model, but this is just relaxation towards thermodynamical equilibrium. So this is really a fundamental principle of information theory, which is we lose somehow information, so we get closer to the equilibrium. So the answer is a little bit. I don't know if we could try to use, as you perhaps you're doing, reformulate to have a better model and to close. I'm not. That's not to close the turbulence problem. This is not what I'm trying to do.
I'm not saying this is it's extremely complicated. The reason is it also related back to the distribution function, because the molecular distribution function, the standard error is temperature, square root of temperature. It is much more broad, and you have to filter it so that it becomes very sharp, because the standard error for turbulence is governed by turbulent kinetic energy, not the temperature. Temperature is much wider, so you have to filter out this dimensional quantity. Otherwise, turbulence, all the turbulence theory, including all the common graph and the subsequent scaling laws, are all screwed up, because you don't have, turbulence only should be dimensionally governed by only the turbulence quantities, not something of the molecule.
Yes, exactly. But this is only, I mean, I applied, so these terms, sorry, just go fast. This is just a footprint on the viscous level, so it's really Navier-Stokes level. Then I don't know if they're relevant or not, but I mean, there are no molecular somehow high order terms here. So the fact is, and one interesting thing is that this equation it looks like a transport equation for the.
Navier-Stokes are special, but if you do it with a original molecular Boltzmann equation.
Yeah, but you have to tell me exactly the assumption I make for which something, because here I really be careful of not introducing any extra assumptions. And what is interesting is this part of the equation looks like the transport of the subgrid scale tensor. So it's the footprint.
Because eventually, I mean, if you don't do any approximation, this is okay. But if you want to come something meaningful out of this.
So I agree that now it's difficult to get meaning of that. The first step is see if these extra terms are not negligible near the boundaries. Then we start doing some question ourselves and doing the model out of that. I agree that could be difficult. But the only thing I want just to add is that these extra terms, they look like a transport equation for the subgrid scale tensor, which is somehow reminds like the Rans modeling of 7 equation models. So it's like a footprint on the viscous stress tensor of this transport of kinetic energy. So it makes a little bit of sense, but yeah, there is still work to do for sure. Thank you.
Yeah. Thanks.
Mer's boundary formulation for that is Boltzmann simulation of the vibrating body.
Thank you for the introduction. Thank you all for attending my presentation. I introduce myself. I'm Alessandro Trotta. I'm a first-year PhD student at the University of Tuscia. Today, I'll talk about an inverse boundary formulation for lattice-Boltzmann simulations of freely vibrating bodies. Here it is a brief outline of what I will talk about. I'll start with an introduction of the topic that I've studied. Then I'll go through the methodology that we have used for the simulations, and then I will go further into the details for the numerical setup. And then I'll show you the results and the conclusions of my work. As we all know, when structures are subjected to flow-related loads that can affect not only the fluid motion, but also can generate oscillations and displacement of the structure themselves. Since we can face with limitation in experiments due to the lack of facilities, but also we can have difficulties to represent the analytical model of the problem that we want to study, we need the numerical simulation to study this kind of problem. The fluid structure interaction problem has been widely studied through the years. One example is the suppression of vortex shedding. And it has been widely studied both numerically and experimentally. In our simulation, we have used the lattice-Boltzmann scheme. These are 2D simulations. We have used the DQ9 BGK single relaxation time. We have implemented the Guo forces scheme to manage the forces in the fluid domain. And for what regards the boundary condition, we have used the Dirichlet boundary condition for the inlet, the non-equilibrium extrapolation method for the outlet, and the free slip boundary condition for the upper and lower boundary. Coupled with the lattice-Boltzmann method, we use the immerse boundary method that is a very useful method to study fluid structure iteration problems because we don't need to remesh our domain, since the key point of the immerse boundary is that we have 2 different grid systems. The first one for the fluid domain that we study with the lattice-Boltzmann method, and the second one used to discretize the obstacle inside the fluid domain. We have different ways to discretize the surface, a sharp interface method and a diffuse interface method, and the latter one is the one that we have implemented in our simulations. In the figure is a representation of how the lattice-Boltzmann method with the immersed boundary method works. The black points represent the fluid grid, and the red points represent the Lagrangian markers that we have used to discretize the surface of the obstacle. There are different formulation of the immersed boundary method. The one that we have used is the implicit immersed boundary method. This is because in this way we can satisfy the no-slip boundary condition. Differently from the other methods available in literature, in this case with the implicit immersed boundary method, we don't know a priori the force correction term to apply in the lattice-Boltzmann scheme. So we need to solve a linear system where A is the matrix which depends on both the distance between each Lagrangian point and on the distance between the Lagrangian point and the Eulerian node. X is the velocity correction vector that is used to compute the forces, and this is what we want to find. And B is the delta velocity vector between the velocity of the Lagrangian point and the interpolated velocity of the fluid in the absence of the obstacle. To solve this linear system, we need to invert the matrix A, and we use the LU factorization using the LAPACK library. Here is an outline of the algorithm that we have implemented to perform these simulations. After the initialization of the lattice-Boltzmann, we apply the boundary conditions. Then we move to the subroutine related to the immersed boundary. We compute, first of all, the kernel function as depicted in the slides. There are several kernel functions available in literature. This is the one that we have used for our simulations. Then we interpolate the density and velocity along the boundary, and we compute the matrix A, the inverse of the matrix A, and the velocity vector B. Then we compute the velocity correction term to evaluate the force correction that we need to spread over the Eulerian nodes. Near the outlet, to reduce the boundary reflections due to the boundary conditions, we have implemented a relation for the Reynolds decay. Is a third-order polynomial, which depends on the Reynolds inside the bulk of our simulation and on the value of the Reynolds that we want on the outlet. Now I'll go through the description of the numerical setup. We started with the simple cylinder test case, where we haven't used any grid refinement and we didn't take into account the gravity force. And the mesh size used for the simulation is 1,080,000 nodes. For regarding the immersed boundary, the obstacle has been discretized with Lagrangian markers that have been uniformly distributed over the boundary. And in the two figures, you can see the dimension of the domain. We have used 40 diameters on the X direction and 30 diameters on the Y direction for the cylinder test case. Then we move to another configuration that is the cylinder with the plate with aspect ratio L over D equal 1, where L is the length of the plate. The Reynolds number for the simulation has been varied from 20 to 200. We have then moved to the cylinder benchmark and studied the case of the cylinder with plate. Then we studied the vibrating cylinder due only to the lift forces. Here are the results of our simulations. In the plots are reported the lift and drag coefficients evaluated with the forces computed with the immersed boundary method, and the results that we obtained are in a good agreement with the one available in literature for both Reynolds 20 and Reynolds 40. So we moved our analysis over the computation of the drag and lift coefficient for Reynolds 100 and Reynolds 200, And we have compared the results also in this case with the ones available in literature. And also in those cases, we are in a good agreement with those. After the analysis of the lift and drag coefficient, we move to a power spectral density of those signals to study the vortex shedding frequency, and so to evaluate the strudel for both the Reynolds 100 and Reynolds 200. And in both the cases, the strudel number is in a good agreement with the results available in literature. With these simulations, we have validated our immersed boundary method. So we move to study another configuration, that is the cylinder with plate configuration. We studied this configuration at Reynolds 200, and here is reported the lift coefficient and the drag coefficient. And then we have compared those results with the cylinder benchmark for Reynolds 100 and Reynolds 200. We can see that regarding the lift coefficient, we have a reduction in the amplitude of the lift coefficient. And for what regard the drag coefficient, the mean value is is very lower respect to the cylinder test case. Regarding the strudel number for the lift coefficient, we can see that the vortex shedding frequency for the case of L over D equal 1 is lower respect to the cylinder benchmark. Here are reported two velocity plots in lattice units obtained for the two configuration cases. So here we can see the vortex shedding frequency and the two configurations. On the bottom left, we can see the cylinder benchmark at Reynolds 200. On the top right, we can see the test case with cylinder with the plate. Then we moved to the case of the cylinder, the vibrating cylinder, due to only the forces related to the lift forces. The displacement of the cylinder has been evaluated only on the y direction. On the x direction has been fixed in the space. And the update of the position has been computed using the Verlet algorithm, integration algorithm. On the bottom of the slide, you can see also the power spectral density of the lift and drag coefficient evaluated with the case of the vibrating cylinder compared with the no vibrating cylinder benchmark. And we haven't seen any huge differences in the spectral density. So to conclude my presentation, we have developed a 2D case, 2D code for the lattice Boltzmann method coupled with the immersed boundary method. We have validated this code using the cylinder benchmark, and we have tested it with the cylinder plate configuration. And in addition, we have developed an algorithm to study the vortex-induced vibration. For the future step, we have developed a 3D code for the lattice Boltzmann method, and we are studying we are implementing the immersed boundary method for the 3D cases. We have already implemented the less Smagoriski model, and we are going to implement also new collision scheme. And the purpose of this work is to be able to study the case of flexible geometries using the immersed boundary method. So for me, that's all. Thank you all for the attention. So it's not so fast because every time that we update the position of the obstacle, we need to interpolate again the position. We need to interpolate the velocity and the boundary. How can I say? We need to perform an interpolation over all the marker points at every iteration. So larger is the obstacle, much higher is the computation time. So for these simulations, I've performed 300,000 iterations, and it took like 1 day. So it's not so fast. For the Albion, the ratio, I don't have the precise number, but probably 2:1 or 3:1. Obviously, only the LBM is much faster compared to the immerse boundary, because with the immerse boundary, we need to compute the matrix A that I showed you previously, every iteration, because it depends on the position of the boundary respect to the fluid domain. So we need to compute this matrix and invert this matrix, and for sure is a huge from a computational time point of view.
I have a question a little bit, why is immerse boundary? And why specifically the implicit? Because as you mentioned, you have to invert the matrix, and so the question could be why not like the multi-direct forcing that is iterative? And the second question, same question, but I mean, I make this question for two reasons. So the first one is a little bit, if you want to go, perhaps it's only one question. If you want to go to higher Reynolds, then the interface is diffuse. So most probably you will have, it's not the most fit method, because you will have a boundary layer and having like a diffuse interface approach with a higher Reynolds that I saw you were showing the picture might not be the best.
So this one.
You know, with the immerse boundary method, you have this force coupling that does not distinguish the inside and outside. So you have very different flow fields inside and outside, like a higher Reynolds flow outside. Then you can have some problems with circulation of the flow inside. So
okay.
There are
So,
solutions to that.
okay. So first of all, we use the immerse boundary method because we don't need to remesh our domain. In this way, we decouple the problem. On one side, we have the definition of the obstacle, and on the other side, we have the classical lattice-Boltzmann method. And we manage the obstacle, the presence of the obstacle using the Guo forcing scheme, because the output of the immerse boundary method are the forces that are diffused over the domain. So as, for example, we want to take into account the gravity force. In this case, we compute the forces that the fluid exerts on the boundary. So this is the first answer. The second one is we use the implicit because, as I said, we satisfy the no-slip boundary condition. We have tried to use the direct forcing, the Peskin method, and also the multi-direct. And from a comparison of the multi-direct with the implicit, there was no such differences in a computational time point of view. So I saw some papers that suggest to use a maximum of 5 sub-iterations for every iteration of the lattice-Boltzmann, and there were no such much differences between both the approaches. But for sure, we will implement a new immerse boundary method for the 3D cases. Yeah, thank you. Okay, so this is only an illustration. This you are referring to this one? And the boundary is exactly the half. Okay, so to compute the interpolation, we use the delta R function. For the streaming step, is everything as it is in the lattice-Boltzmann. So the immerse boundary method, you can see it as a subroutine that you can call or not. So if you don't want to use the inverse boundary method, you can apply the boundary condition and then skip it directly to the equilibrium part. This is the peculiarity of the inverse boundary, that is another grid level that you can consider or not. Yeah. In this case, no, we are not considered the thickness of the boundary. So we consider as an infinitesimally small boundary depicted and described with these Lagrangian points. I know that there are some papers that take into account also the thickness of the boundaries, but we haven't done it in the 2D cases, but we are going to do it in the 3D. Okay.
Thank you very much.
Thank you. Thank you all.
Excuse me, everybody, we have a little bit of time between the end of the session and lunch, which is scheduled during the big forum. And so if everybody could go to the Porteras, which is the big plaza right outside the thing. So if you go down here, take a left, and you exit, and you can all down on the stairs. Thank you.